Okay, X-ray crystallography. So here's some photographs of some beautiful crystals. Here's a snowflake, just spectacular, right? These are crystalline solids. So the molecules or ions in them have a long-range repeating order, and that's why their overall shape has a definite geometric shape to it. So the macroscopic thing that we can see is a reflection of the order of on the molecular level. So X-ray crystallography is a technique that allows us to look at how the molecules and atoms are organized in a crystalline solid. So briefly revisiting, I think this was chapter 7. So electromagnetic radiation includes visible light, and we learned how these electromagnetic waves can interact with each other and form constructive interference, or they can cancel each other out and interact destructively. We watched the video of the guy with the box at the beach, right? So we can produce an interference pattern when light passes through two slits. Do you remember that? Well, we can use this same idea on a smaller scale, where here, instead of having two slits in a slide, we're using the spacing of the atoms or molecules in an ionic or a crystalline solid as the slits. And instead of using visible light, we're using X-rays. So the atoms within the crystal have spacings of about 100 picometers, which corresponds to the wavelength of X-rays. The wavelength of the light has to be similar to the spacing. So we've got an X-ray source coming through a LED screen so that we can focus it, and we've got this beam of X-rays focused on this crystalline solid. As the X-rays go through this acts like a series of slits, and the X-rays are diffracted. Their waves interact with each other, just like the light did in that box. And we get a pattern of X-rays where they have been constructively interfered with, and so there's a larger signal, and destructive interference where there's no signal or a reduced signal. Analyzing this pattern is rather complicated, but computers make this a lot easier. And by analyzing this pattern, we can get information about the spacing between the atoms. So here's zooming in further. So here we have atomic planes. So here's a layer of atoms and another layer of atoms. And the X-rays are coming in, and here's one X-ray, and this comes in, and it hits this atom and bounces off. It's reflected. This atom, this X-ray comes in and hits this one below and is reflected. So if these are coming in the same phase, then whether or not they leave in the same phase or out of phase depends on this spacing, because ray 2 traveled farther than ray 1. And you can do a little geometry. Little geometry. Really? Ray 2 went this much farther coming in and that much farther coming out, right? So you can do all this fun math, and you end up with n lambda equals 2d sine of theta. That is known as Bragg's law. So n is an integer number. Lambda is the wavelength of the X-rays. D is the distance between the atomic planes right here. And A is that distance that X-ray 2 travels that X-ray 1 doesn't. And then theta is this angle. And so what you do is you vary the angle and you look at the pattern of the interference. So typically you look at the angle that produces constructive interference. So that'll get you a bright spot on the detector. And you can calculate the distance between the atomic layers by rearranging Bragg's law. So D equals n lambda over 2 sine theta. X-ray crystallography is used to determine the structure of lots of things. You can use it on simple atomic lattices. You can use it on more complicated crystals. You can also use it on things like proteins and DNA. And this was, X-ray crystallography was a main factor in determining the double helix structure of DNA. Watson and Crick are famous for that. They used X-ray crystallography. This is an example of an early X-ray, what would that be called? I don't know. This is the result of an early X-ray crystallography experiment. We'll say it that way. I don't know what the word is. Anyway, and you look at that and you think, how do you figure out anything from that? Well, it's a lot of geometry. The good news is we don't have to worry about that. Any questions about this idea? How about, what do we have to do on an exam? I would give you this equation, okay, Bragg's law. This is a sort of question that could come up. The spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. So Bragg's law would be given n lambda equals 2d sine of theta. Let's look at the numbers that were provided here. We've got 157 picometers, and we've got 154 picometers, and we have n equals 1. So lambda is the wavelength of the X-rays, so that's 154. The spacing is d. So the spacing is 157. It's telling us that's d. And they're asking us to find theta, the angle. So if we rearrange this equation, divide by 2d on both sides, we end up with the sine of theta is equal to n lambda over 2d. So we could calculate that. So n is 1. Lambda is 154 picometers. Divided by 2 times d, 157 picometers. It's important that the units there match because we need them to cancel out. Could be meters, anything, as long as they're the same. So we've got 154 divided by 2 divided by 157. So that's 0.490. So that's equal to the sine of theta. Sine is a function, and your calculator will do this for you. If we want to undo sine so that we can get theta, we use inverse sine. And it's generally a button either close to the button that says sine or actually the same button. So I'm going to take that value and I'm going to do sine to the minus 1, which is inverse sine, and put that answer in there. And it's going to tell me 29. So theta equals the inverse sine of 0.490, which is 29.4. and that would be degrees. So that's telling me that at an angle of 29.4 degrees, those X-rays are going to give a maximum reflection because they interfere constructively. Any questions? Yeah.
My calculator says 0.512.
Your calculator says 0.512. Well, let me try this again. Are you in degrees or radians?
Radian?
Yeah, it needs to be in degrees. So that would be 0.5 whatever. Radians,
Okay.
yeah. And that's one of those settings on your calculator, especially if you're not taking trig or something, that might get accidentally changed without you realizing it. So glad you asked that. Any other questions?